used to have a sign next to my camera, but I think it fell down during break and I never replaced it. My don't forget to record sign. What is wrong, kitty cat? Let's see here. Get my screen the way I want it. Let's do that. And that. Okay. I think I'm set. Now that my cat has moved, I can move my little standing board. She likes to stand with her tail underneath whatever I want to do because she's a cat and that's what they do. Okay. We are going to talk about chapter 2 today. So actually, let me grab a model kit. I just see that on the top of my own notes, I wrote to have a model kit handy. So we'll see if I actually need it or not. So the way I like to do lectures is with PowerPoint. And so obviously I'm sharing my screen so you can see chapter 2. All of the PowerPoints are up on Canvas. So if you want to print them out or write on them as we go along, they are available to you. I do write on the screen as we go through it. So if you have questions at any point, feel free to unmute yourself, put it in the chat. You can raise your little hand in the participants area. I have the participants window and the chat window open on one screen and then my shared screen up on a different laptop. So hopefully I won't miss anything, but just get my attention a second way if I do miss you. All right, organic chemistry. So when we talk about organic chemistry, I mentioned this on Monday, but it's really carbon-based chemistry. And if you have talked to anybody else that has taken it, or you've read a little bit about it, a lot of people will tell you that it involves learning about reactions. You add these two things together, what does it make? It also involves a lot of mechanisms, which is learning about how the reactions take place. And if we think of organic chemistry as a year-long class, so 2 semesters, that's what about 3/4 of the year will be. The first quarter, so the first about half of our semester, is actually a lot of background information and introduction. So it kind of sounds weird to say this because it's going to last for so long, but it almost feels like we have half of a semester of introductory material so that we can learn about organic chemistry. I also mentioned on Monday that we repeat a lot of the things that we learned in general chemistry and learn them in more detail and then learn them from an organic point of view. And so some of these first couple of chapters are going to feel that way. Our first chapter is molecular representations. So we're going to talk about Lewis structures, which we know, but we're going to expand on that and we're going to talk about it from a organic chemistry perspective. So we have a couple different ways to draw the same molecule on the slide here. These are all representing the same thing. And they're all giving us different pieces of information. So the Lewis structure is the most detailed. And this is what you learned how to draw in general chemistry. It's showing every single bond between carbon and hydrogen and oxygen and hydrogen. And then as we go down the line, we get to the least detailed, which also means it's giving us the least amount of information. When we have just a molecular formula, C3H8O, there's a lot of different ways that those atoms could be put together. So that's not representing one molecule. It's representing a bunch of different isomers that could exist. And then we have the two in the middle, the partially condensed structure. We aren't seeing all of the individual bonds, so it's written as just a CH3 or just an OH. We're not seeing the bonds between the carbons and the hydrogens, so this is kind of the next step. We understand that the carbons and the hydrogens are bonded together. We don't have to show that. And then the condensed structure, this one is kind of weird. It does give us all of the same information as the partially condensed and the Lewis structure. We can't see any bonds. So there's no bonds shown. Now, of course, there are some exceptions to that. If there was a triple bond, a lot of times you'll see it written as a triple bond and then other stuff attached to it. Sometimes even with a double bond. It's not a guarantee. There aren't any bonds that have to be drawn in as lines. The condensed structure is used mostly when we have to type something out. So if you're typing it out and it's, part of a lab report or it's in the text of a book, you can't include a structure as part of a sentence. And so a lot of times a condensed structure is used instead. So we're going to do a little bit of practice here on going from one type to another. Let's see here. I'm rearranging my area. There we go. Okay, so we are going to turn. Oh, let's see. Okay, so this is a partially condensed structure. And we're going to rewrite this as a condensed structure. So just essentially the formula version in order of how they're bonded. So the way that we do this is by using parentheses. And parentheses can be used for two different things. Parentheses can be used if there are atoms that are repeating, like there's two CH2s in a row right there. And the other purpose for the parentheses is when we have something like this guy. So there's these two carbons that are attached to what the rest of, like what we would consider to be the main molecule. This is called a branch. And so we can use parentheses to show that there's this branch attached to our main structure. So here's how we're going to write this. We're going to start with, and I'm starting left to right, so the same as the way I wrote the structure to begin with. We're going to start with CH3. And then I'm going to put my CH2s in parentheses and say that there's two of them. You could write CH2, CH2. That would be completely okay too. Generally, when we're trying to write a condensed structure, though, we're trying to make it as condensed as possible. So it would not technically be wrong, but it might not be best practice. Then I'm going to put CH. And then in parentheses, we're going to put CH2, CH3. And then we're going to end it with CH2, CH3. Now, these parentheses mean two different things. One means the repeating section, and then one means the branch. So if you were to just look at this, how would we know what is what? And the reason why we would know that this one is the branch is because it has that CH3 in it. A CH3 has to be the end of a chain because it already has 4 bonds. It's bonded to the 3 hydrogens and then whatever carbon it's next to. Whereas over here, they are only CH2s. So that means that they have to have a carbon on either side to continue that longer chain. Questions about that? Okay, let's do one more. We're going to go the other direction. Let's see, do I have one more blank slide? I do not. Okay, we'll go down here at the bottom then.
Oh, wait, I have a quick question.
Yeah.
Could you also tell because the CH2 has a 2 subscript after it?
Not quite, because if there was another CH2 right here, like if it was CH2, CH2, then a CH3, we could have CH2 in parentheses with a 2 and then a CH3 next to it. So you could still have repeating pieces as part of a branch. It just wouldn't be able to be the last thing.
Okay, got it. Thank you.
You're welcome. Okay, so let's do, we're going to go the opposite direction. Let's see, let's not make that look like all the carbons in a row. Okay, this one has a little bit of a trick in it, but that's why I'm doing it, so we see it now. So this is our condensed structure. And we're going to turn this into a partially condensed. So I didn't do any examples with Lewis structures or the molecular formula, because really we can take that partially condensed and add in the bonds to show the bonds to the hydrogens. And now we have a Lewis structure. And in full honesty, we don't draw Lewis structures very often in organic chemistry. We use these more quick versions, more simplified versions, and we're actually going to learn how to do one that's even more simplified on the next slide, or the next few slides. Okay, so we have CH3 and then 3 CH2s in parentheses, and then C with an O in parentheses, and then an H. So I know that I'm going to start with a CH3. What is bonded to that CH3? And you can answer in, oh, go ahead.
It's bonded. Oh.
CH2.
CH2. And you can answer in the chat also too. Sometimes that works better depending on where you're at. But what would come after that CH2? Good. Another CH2 and another CH2. Okay, so here's where it gets a little bit tricky. What comes after that third CH2? Maybe this isn't the tricky one. It's the next one after that.
Is it C and then O?
C and then an O. Where's that hydrogen bonded? O is a branch.
O is
perfect.
Gonna be going up.
Okay, perfect. I'm going to move my O.
And that H would go to the side of it.
Okay, we're almost there. There's something that is wrong about this structure. There's something that's making that last carbon unhappy.
The carbon has to
The
have a
hydrogen.
double bond to the oxygen.
Perfect. Now, there's nothing in that condensed structure that tells us that. but we know that carbon likes to have 4 bonds. And so when we draw it out and we see that carbon only has 3 bonds, it's implied that that oxygen is double bonded. We also know that oxygen likes to have 2 bonds. So we can't just have that single bonded oxygen up there because it would make an unstable, it would make a charge structure also. So we have to put in that double bond. And then also we have that oxygen in parentheses. So it tells us that that oxygen is bonded to the carbon and not the hydrogen. If that was an oxygen that was bonded to the hydrogen, we wouldn't have the parentheses there. Okay, questions about any of those?
Would you need to draw the electrons on the oxygen?
That is a great question. And the answer is no. So if we were doing official Lewis structures, yes, we would add in our lone pairs on that oxygen. But this is one of those things where in organic chemistry, we have learned enough. We know how to draw Lewis structures. We know those lone pairs are there, which means we don't have to draw them in. They're now just implied. Later on in this chapter, I'm looking at my notes to see if that's true. Yes, it is this chapter. We will look at how to calculate formal charges. So I know that was part of chapter 1, part of the worksheet, but just kind of a reminder, because now we're also calculating formal charges when the lone pairs aren't actually shown. So lone pairs are not necessary on our atoms, on heteroatoms.
Okay, thank you.
You're welcome. All right, let's talk about how we're really going to draw some structures. So this is a big molecule. And when we draw a Lewis structure for a big molecule, it's kind of crazy looking. It just looks really busy. And because it's so busy and in all honesty, really time consuming to draw, we have another way to draw it. And the way that we are going to draw our molecules in our class is called a bond line structure. It's also called a skeletal structure. They're also sometimes called zigzag drawings. And it looks like this. So it looks like we're missing a bunch of atoms, but every time there's a bend in the structure in that line, it's representing a carbon. So because carbon is the basis of everything we're doing in this class, we know that that's going to be the most common atom. We also know that carbon is almost always bonded to hydrogens. So this carbon right here, we know that it has to be a CH2 because it's bonded to 2 other carbons, which means that its 2 bonds that aren't shown would be to CH2s. And then the carbon that's on the end over here would be a CH3 because it's bonded to 1 other carbon, which means that its 3 other bonds would be to hydrogens. So we're going to talk about some of the rules that go along with this, and then we're going to practice drawing these. So it is called a zigzag structure because when we have sp2 and sp3 atoms, we draw it as a zigzag. So that first structure that's up there has 4 carbons in it. So this is representing 1, 2, 3, 4 carbons. So it starts and ends with carbons, and then each of the little peaks is another carbon. Number 2 on there says, when we draw double bonds, we want them to be as far apart as possible. And the way I always think about it is that you should draw them with the peak. So right here, our double bonded oxygen is going up because that peak is going up. So this is the bad one over here. We don't want to do that one. But let me draw just another zigzag in the middle here. So we could have it going up or we could have it going down, but it goes with the peak. So if our peak goes up, that branch is going to go up. And if our peak is going down, then the branch would also go down. Number 3 says with single bonds, the direction is irrelevant. This is one of the things that can be a little bit tricky when we're first learning it. So these two structures, let me erase that big circle I made. These two structures are the exact same thing. And that can be a little bit hard to see at first. The reason why they're the same is because single bonds have free rotation. So we could rotate those bonds around and have them pointing in a different position. It's like saying that if I put my arms up here or I put my arms down here, I'm still the same person and they're still my arms. They have free rotation, so I can put them in different locations. One way to check this is by counting. And you're going to hear me tell you to count carbons in probably every chapter we're going to do. But we can count them, and there's not, well, okay. I was going to say something and I was going to take it right back. When we count carbons, eventually there is going to be a purpose for it. When we name these structures, there is technically a right and a wrong way to count the carbons. But if we're just doing it for bookkeeping purposes, we're just doing it to see what the structure contains, it doesn't matter how you count it. I tend to go left to right, top to bottom, because that's how I read. But we can just do 1, 2, 3, 4, 5. So I know that that's a 5 carbon chain, and carbon 3 has a branch attached to it. 1, 2, 3, 4, 5. It's a 5 carbon chain, and carbon number 3 has a branch attached to it. So it's an easy way to see if they're the same by just seeing what's attached in what way and see if they match. Number 4. Number 4 says that if a heteroatom has a hydrogen, we have to draw it on. So that's this one down here. So we have our 4 carbon chain again with an OH group. This is called an alcohol group, by the way. When we turn this into our bond line drawing, our zigzag drawing, we can see our 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4. So 4 carbons. There's that OH, that alcohol group on carbon number 2. The only hydrogen that is included in our bond line drawing is the one attached to the oxygen. So hydrogens that are attached to heteroatoms are not implied. They have to be included in the drawing. And remember, a heteroatom is anything that's not a carbon. So for us, that means oxygen, nitrogen, sometimes sulfur, the halogens. X is an abbreviation that it just kind of includes all the halogens, generic abbreviation. So that list is not very long. And in general, it really just means oxygens and nitrogens. We don't see the other ones pop up too often, but we would need to include their hydrogens. And then number 5 is one we've talked about, but only 4 bonds to carbon. And this is one that we can sometimes forget about if we're just starting to draw zigzags and we go too fast. You might end up with a carbon with 5 bonds. So it's always a good thing to remember and to double check. But those are our rules. So we're going to do a couple practice here. We're going to do this in a couple different directions. So I'm going to start by drawing a bond line drawing. And I want us to figure out the molecular formula. So this is kind of just practicing being able to see what that structure is representing and what it contains. We're going to do one more like that. So I'm drawing some that are a little bit different. So the first one contains a ring. So a ring is anytime we have a continuous connecting chain of carbons or of atoms. It's not, we're not using the word ring to mean that it's circular. It can be a lot of different geometric shapes. It just means that they're all connected together. The second one has a triple bond in the middle of it. And notice that when we draw the triple bond, we're not drawing a zigzag, we're drawing it as a straight line all the way across. So our rule, I'm gonna go back up one slide for a second. Our first rule says that when we have sp2 and sp3 atoms, we draw them as zigzags. That rule doesn't say anything about sp atoms, which for carbon means a triple bond or back-to-back double bonds. When those are happening, we're going to draw it as a straight line. This can be a hard one to remember because they don't pop up very often. And then one more, we're going to go from condensed to bond line. Okay. So that first structure, I know it has carbon, I know it has hydrogen, I know it has oxygen. I've done half your job for you. How many carbons are in that structure?
6.
Perfect. There are 6. So I'm going to count going around here. 1, 2, 3, 4, 5, 6. How many hydrogens are in that structure? Very good. There are 10. And then 1 oxygen. We don't need to put the 1 there, of course. So let's talk about those 10 hydrogens just in case you don't see it. The carbons that let's see, let me rephrase that. All of the carbons except for the one I have labeled as number 1, the one that's double bonded to the oxygen, are all CH2s. And if we look at what they're bonded to, each one is bonded to 2 other carbons, which means it needs to have 2 other bonds. So those are each CH2 groups. Questions about that first one? Okay. The next one is just carbon and hydrogen. How many carbons are in that structure? Good. I did not mean for them to be the same, but they are definitely the same. 6 hydrogens. How many, or I'm sorry, I said that backwards, didn't I? 6 carbons, because what I wanted to say next was, how many hydrogens? And again, I did not mean for these to be the same. It's kind of funny that they were. It is 10. So let's talk about why. The 2 carbons on the ends are CH3s. The carbon on the other end is also a CH3. So there's 9 of our hydrogens already. The carbons that are in the triple bond, are just carbons. They don't have any hydrogens attached to them. They already have enough bonds to other carbons. And then this carbon that's right here would have 1 hydrogen attached to it. So there's our 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have all 10 of our hydrogens present. Questions at all about that one?
Yeah, how come the ends of this formula is CH3? I'm just confused on that.
On the left or the right end?
Both ends.
Both ends?
Well, sorry, not
That's
finished
okay.
reading it.
So whenever we have a carbon, it has to have 4 bonds attached to it, right? So if we have a carbon on an end, it's bonded to 1 other carbon, which means it needs to have 3 more other bonds. And so those 3 other bonds are going to be the hydrogens. Does that make sense?
Yeah, that makes sense.
Okay. And then let's look at the last one. So we're going to go the other direction this time. We're going to go from our condensed formula into a bond line drawing. So we have 2 carbons to start with. So that's 2 carbons. It's literally just a line, but it's 2 carbons. And then attached to that carbon is a nitrogen. And then attached to that nitrogen is another carbon. And then an oxygen. Now I do have 2 heteroatoms in there. I have a nitrogen and an oxygen. They each have a hydrogen attached to them. So I need to draw those in. I'm going to draw this 2 different ways. We can draw the hydrogens just right next to those atoms like that. Or we can show bonds. Either way, both are correct, both work, whichever one makes more sense in your brain. I'm going to do a little carbon counting to show you where everybody's at. 1, 2, 3. 1, 2, 3. Questions about that one at all? Okay. This is a table straight from your book of functional groups. So notice that they also have chapters listed here. I mentioned that our first 6-ish chapters or so are focused on a lot of background information, a lot of introductory information, kind of just what organic chemistry is. After that, our chapters are focused on functional groups. And within that functional group, we learn how, or excuse me, within that chapter, we learn how to name the functional group, we learn how to create it through reactions, and then we learn how to react it with other things. And so this is showing us how they're divided, but it's also giving us some names. So these are things you need to know. These are flashcards for sure. So what you need to know is that a triple bond is called an alkyne, and that an OH group is an alcohol. Notice that a lot of these have R's in them. And R is an abbreviation for just a generic carbon chain. Any length, any size, branches, no branches, doesn't matter. It's just saying that there has to be carbons. So for example, the next one on there is an ether. An ether is an oxygen that is bonded to 2 carbons, a carbon on either side. It doesn't matter if it's 1 carbon on each side or if it's 4 carbons on one side and 1 on the other. So if it's symmetrical or not symmetrical, doesn't matter. It just has to have a carbon on each side. So for the first test, you do need to know the functional groups. So you need to be able to look at, I'm gonna go back up a couple slides, look at something like this and tell me that it contains a carboxylic acid and a sulfide and an amide and an alcohol group by recognizing those functional groups within a structure. Too far. There we go. Questions on that? Okay. So we're going to talk about charges, and we're going to talk about carbon with charges, and then we're going to look at some of our heteroatoms with charges. And carbon doesn't do well with a charge. It likes to be neutral. But when we're reacting it, it will end up with a charge as an intermediate step, as an in-between step. So here's our 3 scenarios that can happen. First one, when carbon has 4 bonds, it's neutral. This is what we're going to see 90% of the time. This is a happy carbon. Scenario number 2 is if carbon has 3 bonds, it's going to have a positive charge. So all of the examples up here, these are all positively charged carbons, which we know a positively charged ion is a cation. So the way I always teach my students this is that we can remember that cations are positive because cats have paws. When we put carbon and cation together, these are called carbocations. And this is essentially giving us all of the different ways that that can happen, meaning in this first one, this is a carbon that doesn't have any hydrogens attached to it. So it's a carbon that's bonded to three other carbons, positive charge. In the second example, this would be a CH because it's bonded to 2 other carbons, and that third bond would be a hydrogen. And then in the last example, that would be a CH2, and it's bonded to another carbon as its third bond. And then our last third scenario down here is a carbon that has 3 bonds and a lone pair. This will give us a negative charge. Negative ions are anions, and so when we put that together with carbon, that gives us a carbanion. This list, a neutral carbon, carbocation, carbanion, they are definitely in order of how often we'll see them. So meaning we're going to see neutral carbons the majority of the time. Carbocations would be next in how often we see them. And then carbanions are definitely the least common. They don't show up very often at all. And really what we're looking at here, though, is if we have a structure and it has charges on it, we should be able to look at that and say how many hydrogens are attached to those charged carbons. So the one that I just drew down here, with that negatively charged one, we know that it's going to have 1 hydrogen because it's going to have 3 bonds and that lone pair. And with that positively charged one, it's also going to have 1 hydrogen because that would give it its third bond. Questions about the carbon charges?
Wait, so what happens with that one carbon that has the positive charge? Like, is there anything connected to the 4th bond, or is it just a charge?
So yeah, it's not going to have a 4th bond. It would have an empty orbital that is available to make a bond. So this isn't something that would like last for very long. This would be something that is in the middle of going through a reaction. So it's going to form that new bond very quickly, but at the moment it doesn't have one.
Okay, got it. Thank you.
Anything else? Okay. Then let's look at some other atoms. So looking at oxygen, and this came up earlier with the lone pair thing, but notice right here, writing an oxygen with a negative charge and no lone pairs is going to mean the exact same thing as writing an oxygen with all of its lone pairs and a negative charge. So we don't have to write the lone pairs in, but we do have to write the formal charges in. So if our atom has a positive or a negative charge, that does have to be written in, that does have to be included. The charges can be used to figure out how many lone pairs there are. So the examples that are down here are showing oxygen with a negative charge, neutral, and a positive charge to show us how many lone pairs we would expect to see. And this isn't anything new. This is stuff that we know from general chemistry. It's stuff that was on that first worksheet. It's in the back of the brain somewhere. but it's a good reminder. So when oxygen has a negative charge, that means that it's only going to have one bond and it would have 3 lone pairs. So we know that when oxygen is neutral, which is our next example here, it likes to have 2 bonds and 2 lone pairs. So if it's negatively charged, that means it has an extra lone. Oh, I always hit that button. It's too close to my other buttons. There we go. If it's negatively charged, it has 1 less bond and 1 more lone pair. And if it's positively charged, it has 1 more bond and 1 less lone pair. And that's a trend that happens with all the atoms. We could relate that back to what we saw with our carbon. If we add in lone pairs and take away bonds, it becomes more negative. If we take away lone pairs and add in more bonds, it becomes more positive. So our last one that's on there is 3 bonds and 1 lone pair would give us a positively charged oxygen. All right, we're going to practice this. I'm going to draw some structures. We're going to figure out how many lone pairs the heteroatom should have. I'm going to number them just because it makes it easier to talk about them. Okay. So if we look at that first one, we have a nitrogen with a negative charge. What bonding pattern does nitrogen have when it's neutral? So how many bonds does nitrogen normally like to have as a neutral atom?
3.
3.
Perfect. And how many lone pairs? Good.
1.
Perfect. So there's our neutral nitrogen. So if nitrogen is negatively charged, it has 2 bonds. How many lone pairs is it going to have?
2.
No.
Perfect. And I'm going to put them on the bottom down here because I drew my negative so large. It kind of, whoops, kind of gave myself no space. Okay, so what about the opposite? What about our nitrogen that's positively charged? So it has 4 bonds. It's bonded to 3 carbons and a hydrogen. How many lone pairs should that nitrogen have?
None.
Perfect. I see it in the chat there. Yeah, it doesn't need any. So I'm going to write no lone pairs here just so we know we didn't skip that question. But yeah, if it has 1 lone pair when it's neutral, when it becomes positively charged, that lone pair is going to go away. What about sulfur? So what does sulfur look like when it's neutral? How many bonds would sulfur have?
6.
So 6 electrons. It's in the 6 valence electron category, but it's not going to have 6 bonds.
2.
It will have 2. So 2 bonds. And then in order for us to get to those 6 electrons, how many valence, or excuse me, how many lone pair electrons would it have?
2.
Perfect. Okay, so that's what neutral sulfur looks like. Our sulfur with a negative charge has 1 bond to a carbon. How many pairs of lone pairs should it have?
3.
Yes, I agree. So 1, 2, and 3. And then what about when sulfur is positive? It has the 3 bonds to carbons. How many lone pairs should it have to give it to that, to get it to that positive charge?
1.
1.
Good. Now, you might remember this from Gen Chem, you might not, you may never have been taught this, but when we have atoms that are in the same column on our periodic table, so oxygen and sulfur are right on top of each other, they're in the same column, we know that they both have 6 valence electrons. That's what puts them in the same column, but it also means they have the exact same bonding patterns. So this that we saw right here is the exact same pattern we saw on the last slide for oxygen. So oxygen and sulfur have the exact same pattern for what they're going to look like when they're neutral, negative, or positive. And then what we just saw for nitrogen, if we look at the periodic table, this would be the exact same trend that we would see for phosphorus. Now, phosphorus and sulfur are both a little bit larger than carbon, so they don't form as good of bonds. So we don't see them show up very often. But because we don't see them show up very often, it can be hard to remember what they look like. So if we remember that they're going to look just like their neighbors above them, just like nitrogen and oxygen, it can help us remember that a little bit easier. So this one, I'm going to put here as same pattern as phosphorus. That did not look like as phosphorus. As phosphorus. And then same pattern as oxygen. Sulfur has to have 4 bonds. So sulfur doesn't have to have 4 bonds. Sulfur, in order for sulfur to be neutral, it needs to have 6 electrons surrounding it. So when we have it with 2 bonds and 2 lone pairs, we have the 1, 2, 3, 4, 5, 6. Sulfur can have an expanded octet. So that might be what you're thinking of when we think of extra bonds going to sulfur, but it doesn't have to have that. So this would be kind of like the simplest version of a neutral sulfur. You're welcome. Right.
Would we need to know the neutral version of the atom, or could we just count to make sure that it has like the equivalent of 8 valence electrons or 4 bonds?
Oh yeah, you can still just count them. That works too. But so remember though, with the charged ones, they do still have a full octet as well. So like our sulfur with our negative charge here, 2, 4, 6, 8, it still has that octet around it. So having an octet doesn't mean that it's going to be neutral necessarily.
Okay, thank you.
Can you explain number 2 again?
This one right here, number 2?
Yeah.
Okay, so if we think back to nitrogen over here, nitrogen has 5 valence electrons, right? So we have the 1, 2, 3, 4, 5. That's what makes it neutral with 3 bonds and 1 lone pair. And so in order to have a positive charge, instead of having 5 electrons around it, it would only have 4 electrons around it. And so when it has those 4 bonds, 1, 2, 3, 4, that gives us a neutral nitrogen. The opposite then, if on the top one, if 5 means neutral for nitrogen, 1, 2, 3, 4, 5, 6, 6 would mean 1 extra, 6 would mean negative.
Thank
Does
you.
that help? Does that make sense?
Yeah, that makes total sense now.
Okay. Any other questions on these? So Devin asked a question that kind of made me want to add something else in. So how you would see something like this on the first test is a structure that looks like, I'm gonna move my own little video here, a structure that looks like this, and it would have lone pairs, or it would have a charge, and you're asked to fill in the missing charge, or you're asked to fill in the missing lone pairs. for later tests, that wouldn't be a direct question, but you might have structures with charges, or as you're reacting something, you'll just need to know what those charges are. So we'll obviously get to that much later, but for that first test, you're filling in the missing pieces, either filling in a missing charge and you're given all the lone pairs, or filling in a missing lone pair and you're given the charge. I think I said that both ways. Okay. Let's talk about 3D. I laugh because in chemistry, we pretend that we know how to draw in 3D. So in chemistry, we draw structures in 3D by using dashes and wedges. So I'm going to, actually, no, let's not do black because I'm wearing a black shirt and you won't be able to see it. Let's use some gray here. So that very first structure there, we have a zigzag. There's 2 chlorines attached. The word underneath it is acyclic. So we know that A as a prefix just means not or anti. So it's really just a way to say that it's a chain. It's not a ring. Those chlorines are attached to the carbons in 2 different ways. That one is a wedge. That one is a dash. When we draw the wedge on paper, we don't usually fill it in. We don't color it in. So if I was to draw that on paper by myself, I would draw it like this. And what those 2 symbols are telling us is how the chlorines are arranged in a 3D shape. And I don't know how well you're going to be able to see this. I think I'm going to unshare for a second just so it makes my screen a little bit bigger. Okay. All right. So here's my molecule. The gray sticks are representing the carbon structure. I have a blue sphere that is coming towards you, towards the camera. And I have a green one that is coming towards me or going away from the camera. The blue one we would draw with a wedge. It's coming out of the paper is the wording we use a lot of times. And then the green one would be drawn with a dash because it's coming back. It's going away from you. When we draw zigzags, when we draw molecules, we're drawing them on a flat piece of paper, a flat computer screen, a flat whiteboard, whatever it might be. And so we have to have a way to represent them as a 3D shape because they're not flat structures. So, and I laugh at this because it kind of looks ridiculous. And I know it does not look 3D, which is why I say we pretend that we can draw in 3D. But this is how we represent them to say there's 2 things attached. There's 2 things attached to this carbon right here. The chlorine is the one that's coming out at you, and the hydrogen is going back away from you. It's not great, but it's what we use. It's the best we got. It's a way to represent it. The second structure is a ring or a cyclic structure. And then the last one is called a bicyclic. So we know bi means 2. So it's 2 rings that are combined together. We will talk about these dashes and wedges often. They come up in pretty much every chapter. If you don't see that in 3D, it's okay. It takes a while to be able to actually look at that and believe me when I say that it's in 3D. You just kind of have to accept it, even if you don't quite see it or believe it yet. There's some other ways to draw. The first one is called a Fisher projection. If you are headed on a biology pathway, or even actually chemistry pathway, one of the next classes that you would take after you transfer is biochem. And one of the things you learn in biochem is all of the different carbohydrates. Fisher projections are used to draw carbohydrates most commonly. They are used for other things, but the most common purpose for them is to draw out carbohydrates. Actually, what's drawn here is a carbohydrate. I do not know which one that is off the top of my head. I should have looked, but I don't know. The way that it's drawn, though, is all of these bonds on the spine, so the ones that are coming off of the spine, are all wedges. And then the ones on the tops and the bottom are dashes. So I always think about this as all of those arms are trying to come out and hug you. They're all coming towards you. I heard another teacher describe it as the molecule wears a bunch of bow ties going down the chain. So whatever visual makes sense to you. The next one is called a Haworth projection. This one is also used for carbohydrates a lot. And so both of these, Fisher and Haworth, we use them sparingly throughout this semester and next semester, but they're definitely more common in biochem. So the Haworth projection, we are taking our ring shape, and we have our alcohol and we have our bromine. And so we're taking that ring and we're just turning it on its side. So instead of looking at it from like a front perspective, we're looking at it from a side perspective, so that the things, I'm going to use the word substituents. I think it's the first time I've used that word. When we have things attached to our carbon, the general word for that is a substituent. So we're taking those substituents, and instead of having them be our dashes and our wedges, we're turning it on the side. So those are going straight up and down, and the ring itself is what's a wedge coming out at you. And then the last one is just a different way to draw the bicyclic. So this bicyclic could also be drawn like this. Let me do a little numbering here. And then 7 would be that carbon in the middle. So carbon number 7 is connecting 1 and 4. Bicyclics aren't like their own specific category. It's just sometimes they show up in chapters. They are used when we want to restrict movement a lot of times, because they are pretty rigid structures. So they get used in example problems, but they aren't really like an important topic by any means. So, and they're also kind of a pain to draw. It's especially for trying to draw that version, it's hard to get those angles right. So it has low importance and it's difficult. So I don't use them a whole lot. So I feel like I kind of said this throughout this whole slide. I told you all of these, and at the same time I kind of said, they're not that important. They're important enough that we're talking about them and that they're going to show up occasionally, but they're definitely on the low priority scale. Resonance. Checking my time here. What time are we officially done? I have to look at my cheat sheet. I have to make a cheat sheet for my weekly schedule because I feel like all my classes start and end at like not on the hour. That's all weirdish times. So, okay, we got time. Good. Resonance. You learned about resonance in general chemistry. One of the most common ways that we learn about resonance in general chemistry is something like this. So if we're learning how to draw carbonate, so CO3 2-, we can draw it that way, but we also say, well, that double bond could have gone there, or, oops, that double bond could have gone over there. And so those 3 structures are resonant structures because it's showing 3 equal ways to draw the same compound. that's kind of what we're doing here as well, but we're expanding on it. The reason why we do resonance, the purpose of this is this very first sentence here. Charges are more stable when they can be shared between atoms. When we just draw a structure like the one that's down here, there is a charge on carbon number 3. But if we can draw that structure in another way, if I can move those electrons right there, and now I have a charge on carbon number 1, those two structures are called resonance contributors. What this structure really looks like is that double bond is shared between carbons 1 and 2 and carbons 2 and 3. So we draw it as a dashed line. And that charge is shared between carbons 1 and carbon 3. So we don't draw it as a full charge. We're going to draw it as a partial charge. This guy is called the resonance hybrid. So because that charge can get shared between carbons 1 and 3, it makes it a more stable structure. We can't do this all the time, though. Not everything can have electrons that can move or charges that can be shared. We're going to look at different scenarios of when that can happen, but this is the overall rule. When p orbitals are available, lone pairs and pi electrons can be delocalized. Delocalized is just a fancy way to say that they can be shared. And in order for them to be shared, they have to be able to be moved. So delocalized electrons means that they don't belong to one specific location. They can be moved between locations. So they are shared and movable. I don't know if I spelled movable right. That's okay. Now this only happens with lone pair electrons and pi electrons. So we talked about pi bonds on Monday, but remember pi bonds are when we have a double bond. One of those bonds is a pi bond. If we have a triple bond, 2 of those bonds are a pi bond. So this will only happen with double and triple bonds. So let's look at some more specific examples. And actually, I think I kind of jumped ahead of myself here. I totally did. I did this on the last slide. So let's see. We talked about resonance contributors. I drew it in brackets, but I didn't tell you I was doing that. So when we have resonance contributors, these are our resonance contributors, we sandwich them in brackets, and we use what's called a double-headed arrow in between them. You will learn very quickly that there are so many different types of arrows in chemistry. And this is our first official arrow. So a double-headed arrow is used between resonance contributors. And then when we draw the average of our resonance contributors, it's our resonance hybrid. So we're using partial charges. We're using that dashed line to show those shared electrons. That dashed line is also what we call a partial bond. So it's not a full bond, it's a partial bond. So we're going to look at the different ways we can do resonance, some of the rules that go along with it. And actually, we're looking at one more arrow type too. So to show how those electrons are moving, we use a curved arrow. These are also sometimes called electron pushing arrows. And we're going to use these for different reasons throughout the semester. Every time we use a curved arrow, it's showing electrons moving. And so specifically right now, we're looking at resonance. And I point this out because the rules for how we do resonance and the rules for how we use these curved arrows in the future are going to be slightly different because we're using them for different purposes. But right now we're looking at the rules for curved arrows with resonance. Where we start the arrow and where we end the arrow is really important. So notice our language up here. The end, no, let me rephrase that. The tail of the arrow is what we call where it's starting. This is where, let's try that again. This is where the electrons are starting from. And then we draw the arrow to the end point, or where the electrons are going to end up. So that first example right here, we're starting at those pi electrons at that double bond, and we're moving them to in between carbons 2 and 3. So after that arrow has done its thing, our double bond is now right here, and carbon number 1 would have that positive charge. So when we move those electrons, we are almost always also moving a charge, whether it's positive or negative. So the arrow has to start at electrons. And those electrons could be a lone pair or a pi bond, either one. It's going to depend on what the situation is. And then they're going to end at either an atom. If they end at an atom, it's making a new lone pair. If they end at a bond, it's going to make a new pi bond. We can't start at a sigma bond. So when we do resonance, we can't break a sigma bond. That's what this is showing up here. So that arrow, so it's showing a bad example. It's showing something we're not going to do, but it's showing it start at that single bond or that sigma bond. And when that occurs, it breaks the molecule in half. This is not resonance. I'm not saying this can't happen, but it's not representing resonance. It's representing a chemical reaction taking place. And then the second thing down here says no expanded octets for row number 2. So that would be oxygen, nitrogen, carbon. What it's showing right there is if that did happen, we would end up with a carbon that has 5 bonds. When I took organic chemistry, my teacher always told us that if we drew a carbon with 5 bonds, it would cause the universe to explode. So that is always still what I think about, even when I'm drawing bad examples, is that the universe is surely to explode any moment. All right, we are going to practice. I'm going to draw some stuff and get all my little practice notes here. Let me move my little video. And I'm going to draw my lone pairs in. So I'm going to draw my resonance arrows, and we are going to fill in what the new structure will look like. Actually, I'm going to skip a slide just for a second here. Resonance. Okay, yeah, just this one. Sorry, I have different examples, but I couldn't remember what slide they went with. So we're starting with this one. Now, we know that none of the single bonds are going to break. So how I'm going to start my answer is by drawing in all of those single bonds. I know the lone pairs can move. I know that pi bond can move. But I know all of those single bonds are set in place. So I know that I can start with just my basic skeletal structure. I'm also going to number some carbons just so we can talk about them. Now we have two arrows that we got to deal with. Our first arrow, let's see, we're going to call it arrow A and arrow B. Arrow A, so going from the lone pair on the oxygen, and it's ending at that bond. So how am I going to represent that in my new structure? What's it going to look like down there?
Would it be a triple bond?
So it's not going to be a triple bond, but it is going to create a new pi bond. So we're going to have a new pi bond to be, leaned on my keyboard, a new pi bond between the oxygen and the carbon. So it's ending at that single bond, creating a new pi bond. So arrow A, we went from a lone pair to a bond, which means we're going to make a new pi bond. What about arrow B? Arrow B starts at a pi bond and it's ending at an atom. It's ending at carbon number 3. How are we going to show that in our structure?
Is it going to become a lone pair?
It is going to become a lone pair. So new lone pair. All right. I am going to fill in my lone pairs on oxygen just to give us our full information. So it started with 2. We used one of them to create that pi bond. So oxygen does still have one lone pair. That was a really ugly electron. I can't just put dots because it thinks that I'm like pushing on a mouse button. I got to make them a little weird. Okay. Kind of looks like a semicolon. What about charges? Whenever we move electrons around, we have to look at the atoms that are involved to see if their charges have changed. So the atoms that were involved here are the oxygen, carbon 2, and carbon 3. Who needs a charge? Positive oxygen, totally agree. What about carbon number 2? Is carbon number 2 neutral, positive, negative?
It's neutral.
Isn't it neutral?
Perfect, good. Yeah, so carbon number 2 gained a bond with the oxygen and it lost a bond. So overall, its number of bonds did not change. What about carbon number 3?
I need a negative.
It does need a negative. One way to check your charges as you do this is that the overall charge can't change. Let me tell you what that means. Over here, our original structure was neutral. Nobody had a charge, so the overall charge was neutral. The new structure that we just drew, the overall charge is neutral. We have 1 plus and we have 1 minus. So overall, as a whole, the entire structure is still neutral. So that overall charge has to stay the same because we're dealing with the same number of electrons. We've moved them around and redistributed them, but because it's the same overall number, that overall charge has to stay consistent. Questions about that?
For curved arrows, does the charge always have to change?
The majority of the time. I'm trying to think of an example where it wouldn't change. Yeah, it's so like carbon number 2's didn't change, but the things around it did. So there will be something that will change. And it could even be that the charge goes away. So if we had something like this, so a negatively charged oxygen and a positively charged carbon, if I take that lone pair and put it right there, we get this. And so we go from having a negative and a positive to something that's neutral. But again, overall, this structure was neutral. Positive and negative gives us an overall neutral structure. And we still have that overall neutral. So it could be that the charges are going away, or it could be that they're forming, depending on how those electrons move around.
Okay, thank you.
Anything else on those? Okay. So we're going to look at some specific examples. So we have 5 examples on here of resonance patterns. And some of these we've already seen. Some of it has some new language. So there's a couple structures at the top here for those new languages. And I mean, you guys know this already from taking general chemistry and other science classes, but science classes definitely like to have their own language. And organic chemistry is definitely no exception to that. So a couple new words for us are vinylic and allylic. These both involve double bonds. And I always tell students that the reason why we have all these new words is so that it makes it easier for us to talk about things. So for allylic, it's the atom attached to the carbon that's in a double bond. So instead of saying that's the atom that's attached to a carbon that's in a double bond, we can just say the allylic atom. It gives it a label that makes it easier to discuss. And if something has a label, that means that it's probably important and we're going to talk about it in the future. So if we have a double bond, the carbons that are in the double bond are called vinylic carbons. And this has to do with vinyl. So a vinyl molecule is a bunch of little repeating vinylic units, a polymer. The atoms that are attached, and they can be anything, other carbons, hydrogens, oxygens, nitrogens, it doesn't matter what they are. Whatever those atoms are that are attached are in the allylic position, or we can say that they are allylic atoms. So a little bit of language for us, because look at our first pattern. Our first pattern is an allylic lone pair. So that's this first one down here. That oxygen is in the allylic position and it has a lone pair on it. And that falls into our resonance patterns because we can go from the lone pair towards that vinylic carbon, and then our pi bond can also move. So notice that this one is using 2 arrows because we're using the lone pair and the pi electrons. After we do those 2 arrows, I'm going to draw what it would look like. We would have our double bonded oxygen, and we would have a lone pair with a negative charge on what used to be our other vinylic carbon. The second example or pattern is an allylic carbocation. So this is a carbocation, or a positively charged carbon, that is next to that double bond, so adjacent to the double bond. And again, we have that 1 arrow from those pi electrons. And so after that, and we actually already used this example on a previous slide, but that pi bond moves over and the carbocation then is going to be on the other allylic carbon.
For the first one, for the allylic lone pair, would the oxygen have a positive sign if you're giving away the one of the lone pairs to make a pi bond?
If it was neutral to start with, yes. But because it's negative to start with, when we give away that lone pair, it goes back to being neutral.
Okay, okay. Oh, because of the 4. Okay, that makes sense.
Yeah. All right, number 3 is a lone pair adjacent to a carbocation. So our arrow, we have 1 arrow. It's going from the lone pair towards that carbocation. Let's see, I'm going to draw my structure up here. I'm running out of spaces. So we would have, oh, that was let me redraw that. That was not pretty. We would have a double bond right there. So the arrow is ending at a bond. So that means we're going to create a double bond. The carbon is no longer positively charged because we've given it that extra bond, but our oxygen lost electrons. So it is now positively charged. That was number 3. Number 4, a pi bond between atoms of different electronegativity. So this one is pretty generic, but it just means that we have a double bond, could be a triple bond, but we just don't see those as often. So a double bond between 2 different atoms. So the most common is a carbon-oxygen double bond. So the bond or the arrow is going from the pi bond onto the more electronegative atom. So we end up with a negatively charged oxygen, a positively charged carbon. And then number 5 is very specific. And we'll focus on this more, I want to say next semester, but it might be the end of this semester. And where the divider line is gets a little bit mushy in my head sometimes. The last one, the official label there for it is conjugated pi bonds in a ring. So the structure that's down here, this is called benzene. And it's a 6 carbon ring with alternating double and single bonds. And the arrows are really just showing that we could move all of those pi bonds to the opposite positions. So it would look like this. We're going to spend an entire chapter talking about this type of structure, and it's really the only time that it comes up. So the first 4 are the ones that we will see occur a lot more often. I do have a bunch of practice for this, but we only have a couple minutes left. So I think we're going to start with the practice, not Monday, because there's no school Monday. So a week from today. But let me make sure that's where we're, yeah. So this is a good stopping point for us. Monday, we'll do a little refresher on this because we will practice it. And then we just have a couple slides left in this chapter. And so then we will start chapter 3 on Wednesday as well, which is good because I kind of wanted to get ahead in this chapter because your first test, let's see, I know I have my syllabus pulled up here somewhere. Your first test is 2 weeks from today. So the first test is chapters 1, 2, and 3. Chapter 1 is definitely not going to be a focus. Chapter 1 just kind of shows up because it's part of everything we talk about. Like chapter 1 included formal charges and Lewis structures. We've done all that today already. So I will give you a study guide to help you figure out what specifics out of that. But we will do chapter 3 next Wednesday and then into the following Monday. But I will try and get as much done on that Wednesday so you have the weekend to study everything. Okay, questions before we wrap everything up here?
For the lone pair adjacent to C positive,
Yes.
when you gave one of the lone pairs to carbon, that's neutral now because of the 4 bonds it has?
Yes.
Is that CH2? Would that be CH2 at the top of it, or would it be just CH?
Just a CH. So when it has a positive charge down here, it has 3 bonds. So it already has the 2 bonds to carbon. So that 3rd bond would be to a hydrogen.
Okay. All right. Thank you.
You're welcome. Okay, so go take a couple minute break. Go click on the link for the lab. We'll talk about the first experiment. And I'm also going to talk about how you're going to write lab reports for this class. So it might be a little bit longer than what a normal pre-lab lecture will sound like. But I'm also going to record it. So it'll be there for you in the future. But okay, that is all. I'll see you in a few minutes.
Thank you.
Thank you.
Thank you guys.
Hi, Professor.
Hi.
Just wanted to say hi. kind of meet you in person. Well, not in person, but virtually.
Oh yeah, I didn't give you a chance to introduce yourself. I'm so sorry.
That's okay. I can always.
You know what's funny is I thought about it like in the middle of lecture, and I was going to scroll through to see if I saw your name, and then I was like, and then no, I kept going. I totally forgot.
I kind of had a moment this morning. I was expecting there was like a tab or come for Zoom, but then I realized that your little schedule that you have on the main page, those links are directly to Zoom. And I was like, oh my gosh. And anyways, I kind of joined late, but yeah, I just wanted to say hi. And yeah, I'll just be in more contact communication. I know it's been a hectic week, so hopefully we get
You know, it's the first week. There's always something that happens. So
all right. Well, it was nice to meet you.
you too. You too.
Bye-bye.
Bye. The two of you that are still here, are you still here? Do you have questions for me?